Hello, lovely humans. Jen Foxbot here. Welcome to video 2 on neural networks. Yay! So we're going to get deeper into the mathematics in this episode. So just to prepare you, we're going to look at how we actually represent neural networks with mathematics and how we do computations with neural networks. So we're going to use the same architecture that we looked at last time, where we have 3 inputs in our first layer. Those map to 3 artificial neurons or nodes in our hidden layer, our second layer. And then those map to a single artificial neuron or single node in our third layer or our output layer. And that maps directly to our hypothesis function, aka the thing that the model is giving us as a prediction. Wait a second. Something's missing. Hey, what do you think? Yeah, our bias activation node. So we have a knot, and that goes to our final output layer. But we gotta say, oh, it's part of layer 2, so it gets a fun little superscript of 2. Okay, so if you're like, what the heck is that? What did you just say? Watch video 1. It'll walk you through it. I'm assuming that you know nothing. Well, I'm assuming that you know some mathematics and you're kind of comfy with that. But feel free to ask questions or use your favorite search engine to look things up. Okay, so a couple kind of high level thing to note. So number 1, so the representation A of superscript I and then subscript I, superscript J tells us that this is the activation of unit I of a particular node in layer J. So you can add many different hidden layers, and you would track those with superscript. And then our activation, our nodes are going to have a matrix of weights that we are going to represent with theta, and those are going to be represented by a layer J. And so these will control our function mappings between the different layers. And so these are going to be, so these will help us map from layer J to layer J plus 1, or basically the next layer. So if we're going from layer 2 to layer 3, we would have theta of, well, technically it'd be 1 behind the activation layer, but we'll get to that in a second. Okay, cool. All right. So we'll end with an example as well, because this can be kind of esoteric and overwhelming, but when you apply it to an example, you're like, oh, I see, okay. All right, so each activation layer will have an equation that looks like this. So our first node, A1 in layer 2, is going to equal our sigmoid function, G. Hey, do you remember the sigmoid function? We're going to do a quick aside. So G of Z equals 1 over 1 plus e to the negative Z. Oops, that looks like a 2. Got to add that. Okay, e to the negative Z. Cool. This is going to be very important. It'll keep popping up. Okay, so G of, and here we're going to write down a bunch of terms. Okay, so I hope I gave myself enough space. Of theta, this is our first node, so it gets a 1 here, and this is our first parameter, so it gets a 0. This is our first layer of weights, and this is going to be multiplied by our bias input unit, which I guess is the other thing that we forgot, if that's what you guessed. That's the wrong color. Hold on. Okay. X naught, and then that will map to all of those, but I don't feel like drawing that, so just use your imagination. Okay, and then we're going to do this for each of our input terms. So we have theta node 1, parameter 2, but we count at 0, times x1 plus, and then we just keep doing that, 2, x2, layer 1, and then almost x3, and then layer 1. Okay. Oh, look at that. We did it. And we do this for each node. So node number 2, theta, but this is for node number 2, so we have to track that. X naught to 1 x, whoops, when I go fast I always mess up the subscripts. Layer 1 plus theta, whoops, 2 x2 da da da. Oh, and I put that in the wrong, that's not for x, that's for theta. Oh, these are a little bit big. 2 3 x3, but we fit. Huzzah. Okay. Huh. Okay, and then we do this for the last one. Oh my goodness. Oops, that's not a theta. Hold on. A3 equals sigmoid function of theta 3 0 of 1 x naught plus, okay, you get the picture. It goes all the way to theta 3 3 x3 in layer 1. Okay, it's a lot of terms. Holy stars. Okay, so our hypothesis function. So each of these formulas are going to go into the output node, which is going to determine our hypothesis function. So our hypothesis function, h theta of x, is going to equal our activation node function, which is going to look very similar to this, in fact almost identical except for the superscripts and the subscripts. All right, so sigmoid function theta, this is our first node, but we are in another layer. We are in the next layer, so layer 2 of our weights. There's no weights here, so this is layer 1 of our weights, layer 2 of our weights. That's why they're different. But this is going to multiply. In this case now, it's not, our inputs to this node are these. Those are those nodes. So A naught of layer 2. And then similarly, we add up all of these. So plus theta, whoopsies, hold on, I forgot subscript. This is our first parameter. This is our second parameter in the second layer. So, and then A1 of layer 2 plus theta. Can you guess what's gonna come next? Okay, 1, 2, layer 2 of our second activation node, our second node. Oh, we run into our sigmoid function, and okay, and then 1, 3 of A3, layer 2. Okay, that's a lot of terms. And mind you, these can get very big. These architectures can get very big. So we are doing a baby one, and it's way too long to write out. So this is why coding is really useful, because it is a lot faster than writing it out. Okay, but basically it's important to write these out right, because you can actually see what they look like. It's not some esoteric, it's, you know, it's tangible. It's a mathematical function that we are using that determines the output of a large language model. Okay, and the other thing that I want to mention is that our theta, our first layer of parameters for our hidden layer is going to be a real number and is a 3x4 matrix, 3x4 dimensional matrix. And the reason is because we have 3 nodes. So it has 3 rows of inputs, and there are 4 input vectors. So there's going to be 4 columns. So 1, 2, 3, 4. 1, x1, or sorry, x naught, x1, x2, and x3. That's 4. Okay. All right. So you can generalize this to how big your architecture is, which we'll go over in the next video, is how do we generalize this? We're just going to look at a little baby example first. Okay, so this is a lot of shenanigans to write out. Do we seriously have to do this every time if we're going to write this by hand? Heck no! We're going to be lazy. Of course we're going to be lazy. Okay, so if I take this first equation here, I can just represent this by being like, yo, this is just A1. This is the sigmoid function of z. Like, well, let's just say that this is z1. It's for the first node, and it's in layer 2. Okay, that's so much easier than writing out all of those parameters. This is absurdly easier. Okay, we do the exact same thing for all of the other ones. So z2, layer 2, a3 of 3. Okay, whoops, no. Layer 2, that's silly. G of z3, that's the one that changes. So many numbers going so fast. Okay, and then in this case, You have x is your vector input, x1, sorry, x not x1, x2, x3, and z of 2 is just z1, layer 2, z2, layer 2, z3, layer 2. So this tracks your inputs, and this tracks the number of nodes that you have in a particular layer, in this case, our second layer. Okay, so this is how you represent a neural network. Take a picture. It's small. It's fine. It's fine. And this is, again, a small neural network with only one hidden layer, 3 nodes, 3 inputs. Well, technically 4 inputs. I kind of ignore the bias unit. It's implied. Okay. Also, the one thing that I really want to call out is that you will know X during training. These are your inputs. So in training, you will know X. And knowing these inputs will allow you to propagate through these equations to calculate a form, to calculate these parameters for what your hypothesis function should be. And then theoretically, if you have a good set of training data that gives you a good hypothesis function, when you have unknown inputs, you can put those in. Or I should say, when you have inputs that have an unknown output, you plug those in, and your hypothesis function will give you a prediction for those inputs. Okay, so how do you actually do this? How do you calculate all of these parameters? Well, you just go step by step, right? Okay, so step number 1. Let's see. I kind of ran out of space to write on the board. Well, step number 1. What should we erase? Let's see. Okay, I think that I can erase these because y'all are smart and you know what that is. And I'm also gonna erase. Can I erase? Oh, okay. We're gonna erase that. I'm gonna erase the hypothesis function too because we can always write that down if we need it again. I'm gonna keep those down there though. Okay, so how do we actually calculate these shenanigans? Okay, so first you gotta figure out what is z of 2, and well, what is it? It's just your matrix of parameters. Oh, nope, of the previous layer, that's right, because it's 1 behind, times x for this first layer, right? Because these are your inputs. Okay, so once you have this first layer of your variables, then you go ahead and you can calculate what this activation node is, because this just equals g of z of 2. Okay, cool. So that's not too bad so far. Okay, and number 3. Oh look, I can erase these too. Okay. And then once you do that, then you add your bias unit. Add bias unit. Because we gonna forget. So let's call it out explicitly. Okay, so a naught. That's why we kind of start counting from 0. We're like, wait a second, we have 1 that comes before the first one that we drew. So this is gonna be in layer 2, and that's 1. And just as an aside, this is gonna be a 4-dimensional vector. Okay, and then once we have that, then we can calculate the formula for the next layer. Oh, actually, I should step back and we should calculate what our variable is that goes into the sigmoid function, and that's just going to be the outputs from, I keep forgetting parentheses, that's going to be the outputs from this. So theta can be layer 2 times a of 2. And then finally, 1, 2, 3, 4, 5. Actually, that's not too many steps. And then finally, we can calculate our hypothesis function. La 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 la. That's just going to be the sigmoid function of z of layer 3. Oh, boom, done. QED, or a little box. Boop 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 boop. This is not really a theorem though, so we can't really do that. Okay, what does this actually mean? How do we do these steps? Because it seems a little esoteric, right? Yeah, I got you. Okay, so if you need a break, that's totally fine. You can pause and come back to this later. But let's do a simple example. Simple example. Okay, so I'm gonna erase this to give us some space. But we need the sigmoid function, so I'll bring that little buddy back. If I can grab a piece of chalk. Okay, so g of z equals 1 over 1 plus e to the minus z. And the plot, because I think it is really great to draw pictures. So this is going to be z, and this is going to be g of z. And our sigmoid function looks like this. That's a really bad way to draw it. Hold on, let me try again. Okay, hold on. Now there's an eraser mark there, but that's fine. Okay, so, okay. Oh, crap. Okay, hold on. There we go. Okay, and then this is 1. This is 0, and then this is... Do you remember from the last video? What do you think? This is 1/2, or 0.5. Okay, so, simple example. Ready? We are going to draw a picture because yay, pictures. Okay, so if I grab my fun little colors, we're going to do, actually, okay, so example, we're going to do an AND gate. Or, well, because I do a lot of breadboarding, AND gate, or just an AND function if you prefer programming terminology. Okay, so we're going to have 2 inputs. An AND gate takes 2 inputs, x1 and x2. We'll do little circles because funsies. It has 1 node. Wait, hold on. Let's use purple for our node. It has one node, and then that node goes to our hypothesis function, h of x, h theta of x. And hey, we also have our bias unit, x naught. So that's going to go into our single node, our mystery box that does the important calculation. Okay, so I'm going to skip some steps and just, well, not really skip some steps, but when you are calculating the parameters for a neural network, you need to figure out how much each of these inputs come into play. And so for this example, we're just gonna, if you would do this by trial and error, using gradient descent, et cetera, the previous types of applications that we've learned in machine learning. And or if you have, a simple example for what we're doing, you're just like, oh, okay, we're going to have some parameters here, or some weights here, sorry. This is going to be -30, this is going to be a +20, this is going to be a +20, and we'll see why in a second. The goal right now is not to figure out what these are. The goal is to show you how we get here. Okay. So that means that our hypothesis function is going to look like this. So we have our bias unit. This is going to be g of our sigmoid function. This is going to be -30. Well, actually, let's write this out first. So this is theta 1, 0 of layer 2 times x naught plus theta layer 2, 1, 1 of x1 plus theta 1, 2, layer 2 of x2. Okay, and so then when we plug these in, these numbers are our weights. So this equals a sigmoid function of -30 times 1 plus x. Our second parameter, our second weight is 20 times x1. Sorry, this was x naught. And then plus 20 times x2. Okay, so that is our hypothesis function. All right, so how do we know that this works? This is really what I wanted to show you. Okay, so basically what we would do is we make a table of possible values and we check what the output of our hypothesis function is. Okay, so if we have an AND gate, x1 and x2 can either be 0 or 1. And then for our training data, y equals x1. So that's really how we would get those parameters. And so now we test our hypothesis function to see if our, let's say we guessed these numbers, which is a totally fine way to approach a simple problem like this. And technically that's kind of what training, that's exactly what training is doing. It's guessing these numbers, figuring out how accurate the hypothesis function is with the actual values that it should be, and then adjusting based on whether it's close or not. So what we do is we say, okay, well, what are the possible values of inputs? So we could have x1 is 0 and x2 is 0. And in that case, if we plug in 0 for x1 and x2, we get negative 30 times 1 is going to be negative 30, plus 20 times 0 is going to be 0, plus 20 times 0, also 0. So we get a sigmoid function of negative 30. And now we get to use our handy dandy plot. And so if we have, I should say this is 0. Yeah, the vertical axis is 0 here. Okay, there we go. So if z is negative 30, it's very far away from basically like where the sigmoid function crosses the vertical axis. And so this is going to be pretty close to 0, effectively 0. So, okay, that's good, that's good. An AND function should give us 1 if and only if both the inputs are 1. So that's what we want. All right, so let's check another input. If x1 is 0 and x2 is 1, then we get g of negative 30 plus 20 times 0 plus 20 times 1. So this is going to be negative 30 plus 20, which is negative 10. Again, we look at our plot, that's going to be far enough away that it's effectively 0, or far enough in this direction that it's effectively 0. And we can swap and get the same. x1 is 1, x2 is 0. We're going to get g of negative 10 again 0. And now, if we have both inputs are 1, let's draw that down. That's confusing because I'm starting to get confused with the axis, with my vertical lines. Okay, and the ones. Okay, there we go. All right, so now we calculate our sigmoid function, and we get negative 30 plus 20 times 1, 20 plus 20 times 1, 20, negative 30 plus 40, which is 10. Okay. And so now we're going the other direction. And so if z is 10, we're far enough over, we can safely say that the sigmoid function would be about 1. Boom! There we go. Now we can say QED, I think. So this hypothesis function represents the logical AND function. Huh, super cool, right? So I have homework for you. Do this same example, but with an OR gate. And so what I want you to do, you can use the same architecture. Everything will look the same except for these parameters. So what I want you to do is use your brain to guess what these parameters would be to give you an OR gate. You can totally do it. And then walk through and check your answers just like you would do. For an OR gate, the output is going to be 1 unless both inputs are 0. Or I should say, the output is 1 if any of the inputs are 1. Boom. Okay, that was a lot, so I'm going to stop for now. Thank you for hanging in there with me. Or if you need to pause and come back or whatever, good job. I'm glad you came back. Please let me know if you have any questions about how we do model representation and some calculations with neural networks. In the next video, we're going to look at how we generalize this to different types of neural network architectures, because again, this is just one very specific architecture, but it's useful for understanding how all of this is laid out. All right, Thank you for watching, and we'll see you next time.